Complex numbers. All right, so we're going to talk about complex numbers. So complex numbers have a form of z equals a plus bi, where both a and b are real. And we define I to be, I is defined to be I squared is equal to square root of 1. Most of you guys defined this to be I, which is fine. It's 100% fine. This is a little bit more correct and precise, but um, don't worry about the subtle differences. In engineering, sometimes you guys use J as the imaginary unit, if I'm not incorrect, because you reserve I for current. So maybe only electrical engineers have to deal with that, right? So if you see J as an imaginary unit, um, I think that's the electrical engineers who do that. Um, I don't love the notation of I because you also have I hat, which is the X vector, right? And so sometimes some of the standard units get used a lot. So one thing to be very careful for when you move forward in your college career is to pay attention. What does the notation mean? Because it'll mean different things from book to book and from class to class. So just be very careful. Real quick, A is the real part. So the real part is A. The imaginary part is just B, not B, not BI. And let me be very clear about this. So here, if I'm going to identify the real and imaginary parts of each number, here, the real part of this number is 5. The imaginary part is 3. Not 3i. It's not 3i. It's just 3. So the imaginary part does not include the imaginary unit. So the imaginary part is the real part, is the real number, let me be clear, B, that is with the imaginary unit. And so it's kind of a subtle thing. So here, RE is how we abbreviate the real part. IM is how you abbreviate the imaginary part. So the real part here is nothing, right? So I could technically write this as 0 plus 3.1 I. And so the real part here is 0. So if you don't see the real part or the imaginary part, go ahead and just write it to be 0. The imaginary part here is 3.1. Again, it does not include the imaginary unit I. And if you see something like this, you're going to have to just do a little math. So here is 3 halves, and the imaginary part here is 1. So 2 over 2. Okay. All right, so if you're adding and subtracting complex numbers, so if you add and subtract complex numbers, you just do it the real parts with real parts, imaginary parts with imaginary parts. I mean, this is a fancy way of saying that mathematically, but you add up the real parts, you add up the imaginary parts, and if you subtract it, you subtract the real parts and you subtract the imaginary parts. So when we perform this operation here, if we're going to add these two up, I'm going to add up the real parts. So I'll have 2 plus 6. I'll be a little pedantic for a second. And then here I'll have 3 minus 3. So 3 plus a negative 3. I. So 2 plus 6 becomes 8. And the 3 minus 3 is 0 I, or you can just leave it as 8. Here, if we want to do this operation, what I would do is go ahead and move in the negative sign. This one you have to do. This one, we'll go ahead and do it as well. And so this becomes minus 3 plus 3i. So here I move to the negative sign. Here I'm going to move it in as well. So I'll make this plus. So this becomes negative. So this negative times negative becomes plus 2. And the negative plus the 4i becomes minus 4i. So here I've written it all without parentheses. Now I can just add up the parts. Negative 3 plus 2 becomes minus 1. And then 3 minus 4i becomes minus I. Okay. Now, if you have a whole bunch of stuff all together, just do what I usually do. Just do the real parts first and the imaginary part second. So I have 3 plus 6. So 3 plus 6, and so that gives me 9. And here I like to cross off things because I just make sure I got everything. So the 7i minus 2i plus 2i, well, the plus 2i and minus 2i just cancel each other out. And then I just left with the 7i. So here I've used all my terms. Sometimes it's not amazing to cancel, but if you're using a digital format, after you cancel everything, you can just erase all your cancellation marks and see if you get back what you want. Okay, so that's the first page. I'll let you guys finish copying that down as I take a drink. All right, let's go to the second page. All right, so let's talk about powers of I. All right, so powers of I. So notice that, notice the patterns of power of I. So here, if I have I to the first power, well, anything raised to the first power is just itself. I squared by definition is -1. I cubed would be the same thing as I times I squared. So it'd be I times -1, so it'd be minus I. And I to the fourth would be the same thing as I to the 4, or I squared times I squared, which would be -1 times -1, which gives me +1. And then it goes I, and then this. And so it just kind of repeats this pattern. So it just kind of repeats this pattern here. Okay. And so I to the 7th, just for our own, I to the 7th would be minus I, and then I to the 8th would be 1, and then I to the 9th would be, minus I would just be I. So how do we do this? So here I to the 9th, here we just calculated it out just by continuing. We got this equal to be I. So how do we do this? And so let me give you a little nice thing to do. So here we can divide the exponent by 4 and look at the remainder. And let me explain to you what I mean right here. So here if we have 47, so let's divide the exponent by 4. So here I'm going to take 4, divide, division, I look at like division, good old long division, right? 47. So this goes in once. I left move 0, drop that down to 7. This goes in one more time. And then I'll have a remainder of 3. So 47 divided by 4 is 11, remainder 3. So let me rewrite this. Let me rewrite this real quick. So I can write this as I to the 4th to the 11th power times I to the 3rd. Now, does this equal the same as this? Well, 4 times 11 is 44, plus 3 is 47. So these are equivalent. And then here, what's I to the 4th? Well, I to the 4th is 1. So 1 to the 11th power times I to the 3rd. Well, I to the 3rd is -I. So let's just go ahead and plug that in. Well, 1 to the 11th power, well, that's just 1. And so this just becomes minus I. Now, do we need to do all these steps? Not necessarily. Oh, real quick, I to the 0. This is 1. Let me give us one more. Let me do I to something ridiculous. Let's say 206 power. What's I to the 206 power? Well, here, if we divide this by 4, we'll have remainder of 2. And you should be able to do this in your head without. So 200 goes cleanly into 4, right? And then another 4 So that gives me, so this has a remainder of 2. Do I need to write out all this? No, just look at remainder, just look at I squared, and this will be -1. Okay, so here, when I divide this by 4, this will actually just be equivalent to I squared, right? So since this repeats every 4, you can simplify and use that. Does that kind of make sense? You'll do 1 or 2 problems like these. You divide by 4, and then whatever the remainder is, if it's 0, it's 1, right? Let me write that in. All right, I to the 0. So if it's 0, it's 1. If the remainder is 1, it's I. If the remainder is 2, it's -1. If the remainder is 3, it's negative I. And since you're dividing by 4, you should never have a remainder of 4. And since these need to be integers, since all these are integers, you're only going to have whole number of remainders. Okay. All right. So this might be new. I don't think they really teach that in high school, but it is taught often in college, and it's something useful to know. That way, no matter what power of I, you feel comfortable in dealing with it. All right, so let's talk about multiplication complex numbers. So if I multiply complex numbers, here we just FOIL. So we'll have A times C, A times DI, plus B times CI, plus A times BI squared. But notice BI squared is -1. So our real part in this case would be AC minus the -1 will make this negative BD. And then we'll add AD plus BC plus I. Do I memorize this formula? No, I really don't. I just kind of just crunch through the numbers. So let's just crunch through it. And so here, let's just start doing some crunching. So here I'll have 2 times 6. So let's go ahead and FOIL this. So 2 times 6 would be 12 plus the outside. So 2 times -3i would be plus or minus 6i. Plus here we'll have inside. So 3i times 6. So that'll be 18i. And then here we're going to have the last. So 3i minus 3i. So this would be minus 9i squared. Okay. So let's go ahead and just get everything down to the simplest power. So either of I. So this I, squared. This I squared just becomes plus 9. Okay, because I squared is -1. Now we just add it up. So 12 plus 9 is 21 plus 12i. Okay. All right, so here, and that's complete. So here we're just going to multiply 3i in. So negative 3i times -3 is minus 9i. And then here we'll have plus 3 times that would be 12i. Oops. Squared. So 12i squared is -12. And then, whoops, minus the 9i. And conventionally, you write the real part than the imaginary part. So that's why I kind of switched what order they're in. Okay. All right, so what happens when we have something cubed? Well, we do what we did if it was just a binomial, or if we cubed a binomial, right? We just write minus 3i times 2 minus 3i times 2 minus 3i. Okay. Now what I would do is I do this first part here first. So do this down. So here, FOIL. So I'd get 4 minus 6i minus 6i plus 9i squared. And then here we'll multiply that by 2 minus 3i. We'll simplify this down. So this becomes -9 plus 4, so it'll be minus 5. This becomes minus 12i. And we're going to multiply this by 2 minus 3i. So let's go ahead and FOIL again. So this becomes minus 10. All right. Outside, so negative 5 times this. So it'll be plus 15i. Negative 12 times 2 would be minus 24i. And then negative 12 times negative 3 would be plus 36i squared. So if I simplify that, this becomes negative 36 plus the negative 10 becomes minus 46. And then negative 24 plus 15 gives me minus 9i. Okay. Any questions on these three? No. You guys are going to be real quiet today. That's fine. That's 100% fine. All right, so let's talk about conjugates. Where did the 5 come from? Oh, this negative 5. Thank you. That's a good question. So here, this 4, I have a 4 here, and then this right here. So 9i squared is equal to minus 9. And so the 4 plus the negative 9 should be minus 5. I assume this is the 5 you're talking about? Yep. Shouldn't it be a 4? No, so hold on. Yeah, because this is, go back. So this I squared makes this, so it'll be 4 minus 9, which equals minus 5. Okay, does that make sense? I think so. Yeah, it makes sense. Okay, good. Please do ask questions. Please. If we were in a classroom, I'm like, well, if everyone's so bored, why don't someone come up here and do a problem? And then presto, they're less bored. I actually don't call out students, but I jokingly do say that and see if people wake up, though. All right, so let's talk about complex conjugates. So we've talked about conjugates before in this class. So if you have a plus bi, it's the conjugate with written on the bar is a minus bi. And the reason, another reason is it clears out, conjugates tend to clear out the strangeness, right? Tends to clear out the strangeness of, so here when we did conjugate radicals, we got rid of radical. Here when we do conjugate complex, we clear out the complex number and brings everything to real. So that's kind of reason we do this. So here we're just going to find the complex conjugate. So here, if z is this, so the real part remains the same, and then whatever the imaginary part is, we negate it. So if it was negative before, it becomes positive. So here's the conjugate for that. Here, if it was positive, this would be 3 minus 4i. And here, if there is no real part, you just negate the imaginary part, and that's it. So minus 21i. Okay, so that's the end of this page. So I'll let you guys copy that down. Then we'll get to our last page of notes for the day. All right. Right layer. All right, so let's talk about division. When we divide complex numbers, usually what you do is you just multiply by the conjugate. So conjugate over the conjugate. So this is, again, we're multiplying by 1. So most of the time with fractions, we'll multiply by, I'll go back to that. Multiplying, when we're solving things with fractions, we're always multiplying a fraction by 1. So it's the same thing over the same thing. Because if I multiply by 1, we're good to go. Okay. So here we have, so we're going to be using our conjugates here. And so we use that to perform given operations. So let's go ahead and do that. Let's just do this real quick. So here, so we multiply by the bottom conjugate. So the bottom conjugate here would be 1 plus 2i. 1 plus 2i. All right. So let's go ahead and do this. So up top, we'll need the FOIL. So I'll have 3 plus the outside should give me 6i. The inside give me plus 5i. The last two give me plus 10i squared. And then here on the bottom, it's just this number squared plus this number squared. Doesn't matter what it is, that's what we're going to get. So we'll get 1 squared plus 2 squared. All right, let's go ahead and simplify this. So here, this becomes negative 10 plus the positive 3 gives me minus 7. And the reason this becomes negative 10 because I squared is negative 1. So you switch this. Plus 11i, 5 plus the 6, all divided by 5. And just to split it into the real and imaginary parts, I'm going to write this as negative 7 over 5 plus 11 fifths over I. So here's our real part, and here's our imaginary part. Okay? So what is the complex conjugate of 4i? I'll have you guys write that in chat, so at least know somebody's paying attention. What's the complex conjugate for 4i? Minus 4i, yeah. So we're going to multiply both sides by minus 4i. So when we do that, what we're going to get here is, so we get minus 28i, and then we'll have minus 12i squared all over, so the real part technically 0, so we 0 plus 4 squared, so we'll have 4 squared here. We'll simplify this out. So this negative 12, so this I squared becomes negative 1, so this becomes positive 12. So we negate this. Minus 28i all over 16. Here, there's a 4 everywhere, so we can simplify this to 3 plus, or 3 minus 7i divided by 4. Or if we want to be very particular, we can write this as 3 minus I. Okay. Notice in this case, it would have been perfectly valid just to multiply everything by an I. You would have gotten an equivalent answer here. So. All right, so why do we introduce it? So 90% of the time, when we use this in real life, it's because of this. Let me rephrase that, not 90% of the time. 90% of your early math career, you'll use this. If you are optical engineer, your I will most often be used as your extinction coefficient on your optics. So I'm trying to remember it, my brain just died. On your refractive index, the imaginary part represents how much of it gets absorbed by the material. So, I'm trying to think. My brain's a little fuzzy. But yeah, that's about where it ends up at. So you won't have to worry about that for much. But most of the time in your math career, this is what you're doing. If you're going to have minus 7, and you're going to well, I want to convert this over to minus I squared root 7. And so we're going to do this, and we're going to do this to perform these operations. And I want to do this very clearly because if you do stuff, if you don't do it this way, you'll make mistakes. And let me explain why. Here, the correct way to do this is I'll have I square root 2 times I square root 3. And then I can rewrite this as I squared square root. And remember, square root 2 times square root 3 is the same thing as 2 times 3. And bring it in. And then we can define this to be negative square root 6. Please, please, please be very, very careful. This is the correct answer. Okay. What you'll be tempted to do is to take negative square root 2 times negative square root 3. Write this as the product of negative 2 times the product of negative 3, which gives you the square root of 6. This is wrong by a negative sign. Okay. You cannot do this since since square root of 2 is not a valid square root in the sense that you can, and it's not a valid number. So since this is outside its domain, this is not an allowed operation. So we're going to have to introduce the imaginary unit in order to work with it. Okay. So do not do this. This is bad. All bad. Okay. All right, so let's work through some things. All right, so let's do this. So here, if I have this, I'm going to write this I'm going to simplify this just to make my life easier. I'm going to write this as, let me go ahead and do this. So I'm going to write this as 2 square root 3 minus square root of minus 3 plus 3 plus the square root of minus 4. Right, so I'm going to make that my first step. Actually, let's take out the square roots. Let's take out the I. Let's make that our first step. So my first step is going to simplify all my radicals. So here I have 2 square root of 3, because here I can I can write square root of 12, for those who forgot, can be written as square root of 4 plus the square root of 3. The square root of 4 is 2 minus, I can pull out the I. That's what our thing is here, plus 3. I guess with square root of 4, let's go ahead and simplify that as I times 2. That's actually a weird way of writing it. Let's write it as 2I. But usually imaginary units at the end. Okay, so from here, just to make my life easier, I have a square root of 3 everywhere, so I'm going to just pull that out. I'm just going to pull that out for a second. And so I'll have 2 minus I times 3 plus 2I. And then I'm just going to FOIL that. So square root of 3. So 2 times 3 give me 6 minus, plus 4I minus 3I minus 2I squared. All right, so 6 minus the 2I squared, so this I squared becomes negative 1, so this becomes 2. So 2 plus 6, so it'll be 6, and then multiply by the square root of 3 plus, we have a 4 here, minus that, so this becomes 1 times the square root of 3, square root of 3I. Okay. So why do we introduce this? The main reason we introduce this is so we can solve quadratics. Right? We need to be able to solve some quadratics. And so here, I have x squared equals 2 minus 4, means x is equal to this plus or minus the square root of minus 4. I mean x is equal to plus or minus, oops, we don't equal sign, 2i. So here we can solve this completely, getting 2 answers. I think this is the fundamental theorem of algebra, is that any polynomial will have n roots to it. Any polynomial degree n has n roots. And this is allowing you to find all the roots of the zeros. Here, if we do this, we can't compute this, and so we just throw it to the quadratic formula. So negative 4 plus or minus 4 squared minus 4ac all divided by 2a, which is just 1. So if I simplify that out, I get minus 4 plus or minus the square root of 16 minus 20, so it'll be minus 4 all over 2. So this is x is equal to minus 4 plus or minus I is 2i all over 2, or negative 2 plus or minus I. Okay. Past the end of these notes.